Okay, they connected me. So this is a typical cross-section, well, not necessarily a typical cross-section, through a what turns out to be a Peraluminous Copper-Oxide Greisen deposit at the Coronation Prospect in La Paz County, and that's in our book on La Paz County. And one of the things that was unusual about it was Magma Chem has spent its whole career trying to figure out relationships between composition, both mineralogical and chemical, of various plutons all over the world, even down to peridiotites now. And so peraluminous plutons we had inventoried in Arizona a long time ago, but we never saw a case where we had a significant amount of copper until this thing turned up when Merrill Palmer found a bunch of large quantities of chrysocolla-bearing boulders over a large area in a earlier stage peraluminous biotite granodiorite. And that really piqued my curiosity, because that was an anomaly to my understanding of oxidation of copper and porphyry copper deposits in particular, and ultimately it led, when Jan and I were working on Pinal County, to the development of a new model, Peraluminous Copper-Oxide Greisen deposits. And an investigation of the Gunnison copper-oxide deposits strongly confirmed the model. I don't know, I fixed that slide and somehow I got back in there. But that's going to be a major, giant copper deposit, potentially. And it's as big as many of the porphyry copper deposits. But they're associated with a whole different plutonic sequence, which we'll get into right now. Now this is a typical example of them, although it's a little more scenic than most. It's called the Texas Canyon Pluton. You guys, I'm sure, have all driven through it on I-10. Hopefully they don't make it a national monument or something. But it has, as we'll see, a lot of copper oxide, and it's not just secondary. I think it might be primary, and we'll get into that in a minute. So this is a bit of a petrochemical thing that is, anybody that's familiar with magma chem knows about the peraluminous metaluminous distinction, and that's determined on an ACNK, which is versus silica diagram. An ACNK stands for molecular aluminum over molecular calcium plus sodium plus potassium, all as oxides. So you have your standard chemical analysis, you calculate that ratio from the petrochemical data, and you can see that there's quite a difference between peraluminous plutons and metaluminous plutons. Now I'm showing here a suite of type data from the metaluminous calcalcalic porphyry coppers, and we're talking about places like Morenci, Ray, classic porphyries. And that's what we refer to as classic porphyries. But this new one, Peraluminous Calcalcalic Greisen coppers, is as you can see, is way more aluminum rich relative to the alkali oxides. And it only consists of later stage 3 and 4 in terms of differentiates, fractional differentiates, whereas the metaluminous sequences, if you're lucky, like in the Wickenburg batholith, you might find a pyroxene gabbro, but mostly you'll find hornblende pyroxene quartz diorites, such as the tortilla diorite, and then the biotite hornblende granodiorites, which is stage 2.5. And then if you get into the stage 3, which didn't get on here, we had to move pretty quick, which is the biotite granodiorite. And that particular rock system is what is associated with porphyry coppers, spatially and temporally. As we'll see, the biotite granodiorite stage 3 in the peraluminous is also associated with copper, and I think it has to do with biotite leaving the system, and then that creates a water crisis, and then you push a lot of copper out into that stage 3 fluid release. But if you do evolve at stage 4, which is the muscovite granite, leucogranite, like you have up near Mount Lemmon or at Windy Point, you can get beryl and more commonly tungsten, typically as huebnerite or scheelite, Greisens. But as it turns out, there's a lot of greisenous quartz muscovite pyrite alteration associated with the stage 3, and that's particularly common at Gunnison. Okay, next. That's superimposed on typically an earlier quartz orthoclase magnetite alteration. This thing is sticking on me again. Where's our tech? Okay. So that's what a typical peraluminous calcalcalic stage 4, that's the classic garnet schlieren from near Summerhaven, versus a metaluminous hornblende biotite granodiorite, that's from the Leatherwood. That's just down the hill and is associated with the Marble Peak copper skarn system in the Catalinas. So pyroxene and hornblende are typical of the earlier stages in copper-related metaluminous sequences, and we're just going to simplify it for the rest of the talk as metaluminous porphyry coppers. That's the classic, and then these peraluminous guys. Yeah. Go to the next slide. This thing, okay. So I'll just have him advance it?
Yeah.
I'll just hold my hand up. Okay. So here's the main player in the main copper ore mineral, and this is going to be controversial because, including myself, almost everyone thought that was a supergene mineral. But the funny thing about it is it commonly coexists as a globular, almost colloidal gel associated with primary specular hematite. And that's not the typical thing you see in an oxide cap over a standard porphyry copper, a metaluminous porphyry copper. In these systems, these are the peraluminous plutonic environment in general is a low sulfur system. So you have rare pyrite or chalcopyrite. Chrysocolla is by far the most common one, but you do get minor malachite and azurite. Leached caps is over the tops of higher sulfur porphyry copper systems, where you have acid generating power with a pyrite oxidation, can make chalcocite blankets. Number of these guys have been drilled, and nobody has yet to find a chalcocite blanket. And that's a major distinction between the two. And as we noted, primary chrysocolla may have initially formed as a non-crystalline high-temperature colloidal gel. As a mineralogical oddity, there's a niobium-rich rutile that occurs that's been identified at Gunnison. Whether that's a more general characteristic or not, but I'm not aware of that kind of a rutile in the porphyry coppers, so it's kind of interesting. Next. Okay. So here's the example of the big guy, again at Texas Canyon. I'm sure many of you may have actually been to Gunnison, which is this guy right here, and then Johnson was actually mined in the open pit. This will be an open pit. And it's a large system. There's about 3 million tons of copper that have been drill identified or mined. And I think, whoops, go backward again. Backward again. Okay. The Centurion thing, they've got a little prospect that they're starting to develop called South Star. This is Excelsior Resources. And I think that's going to be a lot bigger. Potentially you have an arc of peraluminous copper as low temperature skarn assemblages all the way around the northeast and southeast contacts of the Texas Canyon Pluton. That's a lot of copper, and Fitzpatrick did a mass balance study and figured out that there might be at 20 ppm copper, when you separated the 20 ppm into the low ppm biotite apolites that are intimately associated with the copper there, you could have as many as 8 million tons of copper. And the current resource has been defined as a large volume chrysocolla dominated with hematite, lots of specular hematite, and magnetite, another iron oxide mineral, ore body. And I think if they try to find a chalcocite enrichment blanket there, they have drilled a few deep holes and they've yet to find one, and I think they're not, because this is not that kind of a system. But who knows, I could be wrong. I've been wrong before. I never, like I said, this is a new model that escaped our extensive compilations. Okay, next. Another thing that is potentially unusual about these things is the way they oxidized. If they're in the surface environment, they interact with the meteoric waters, which is interacting with rotting cacti, fleshy cacti. And you make glycolic acid, and then that interacts with the chrysocolla, and you make really odd glycolate minerals. So far, the mineralogists have had a ball with these things. They have 9 new glycolate minerals that are new to science, that are all from the Push Ridge case history. And whether that is, there's only one case history of this so far where these unusual minerals have been found. So whether that generalizes into a more generalized scenario, I don't know, but could be. Next slide. I won't spend, Jan told me not to spend much time on this one. This just shows how you could start out with wheelite, which is a acetate mineral. Throw acetic acid on it, get it in the meteoric system on in this case a rotted prickly pear on Push Ridge, and then that reacts with chrysocolla and then you can make oddball. The main mineral there is lazarescite plus chalcedony, which is the white mineral in the lower. Come on. This thing doesn't want to. Oh. Back it up one. So we're looking at this. So the lazarescite's the blue. This breccia fragment was interpreted by Ron Gibbs, who took the picture, to be originally chrysocolla, but it's desiccated into a white material, which is a combination of chalcedony plus gibbsite, if you look above the picture there. So some very oddball mineralogy might be a part of the oxidation sequence in these things. But only so far we only have one case history at Push Ridge. Okay, next. So this just simply shows when we got into Pinal County, we started seeing these things. The first thing we started looking at was Perry Durning's old Little Hills chrysocolla mine, which was originally used as flux from the San Manuel smelter. And as it turns out, it's associated with the Little Hill muscovite elasticite and related rhyolite dikes, pegmatites, and a transition gneiss. It's now yielded a 63.8, not a very good uncertainty at 17.2, but it's roughly in the peraluminous category. Now these things typically form later than the metaluminous. We'll see what their tectonic setting is in a few minutes. A direct analog for this thing is coming up on the Mogul Fault, which is a boundary of the Santa Catalina lower plate metamorphic core complex, formally talk. We don't use that term anymore. But North Star is an analog, could be a good play, should be looked at more. Newman Peak there's a number of occurrences in the main Picacho Mountains. Durham Hills is an interesting chrysocolla occurrence with hematite. That's the main assemblage that you see in these things, is chrysocolla and hematite, plus or minus other things. And in this case, you had a little bit of chalcopyrite and a little bit of chalcocite, but not enough to make a difference. Suizo, which is just down the hill or across the valley from Durham, is in a leucocratic muscovite biotite granite. So a completely different set of granitoids are associated with these things. As we'll see, they tend to inhabit these lower plates, which we'll get into when we get into the tectonic setting. Red Hills is up in Pinal County, east of Florence, associated with a bunch of quartz-rich rhyolitic dikes that have been dated at 70.7 Ma. And then the 96 Hills 2 mica granite, which is close to the Red Hills. A teacup pluton also. It's another peraluminous granite and associated with these things. They just start showing up again and again. And as Red Hills was heavily drilled, and they went deep trying to find that chalcocite blanket, never did find it. They were in roughly 1,000 feet of chrysocolla hematite. Not all continuous, but erratically present over a big thickness and a big tonnage. Hayden Peak is another one of these things up in the Sacaton Mountains, northeast of Casa Grande cactus deposits, which are well-known metaluminous porphyries. That thing we're calling the Bianco. Sacaton Butte southeast is another one. These are all relatively small occurrences. I don't think they're going to do much. Casa Grande Mountains is another one. A bunch of these are mostly in pegmatites and in veins in the Pinal schist, and I'm guessing that those are probably laramide. And Estrella Sunrise Mine in the Sierra Estrella Mountains, another one of these aphlite pegmatite things with chrysocolla, and possibly analogous with Signal Peak. And again, we have much more details on this that we're going to come out with in the Pinal County book, which will be out hopefully in November, late November. Next. Now caused us to say, okay, what else is maybe out there? And so we went back to Cochise County. And lo and behold, we looked at Texas Canyon again and realized that that pluton was a big old peraluminous granite, with the stage 3 being associated with the biotite granodiorite and biotite aplites being associated with this chrysocolla, hematite, magnetite skarn, and then a stage 4, late stage thing, muscovite, garnet, aplites associated with tungsten veins. And that's another thing that shows up in these things that you don't see in the typical porphyry, is tungsten mineralization. Quite a different animal. Then you have, well, we talked about Gunnison briefly. Carlotta. Now that's another one. Up in the Globe, Miami area. And there's a peraluminous granite up there called the Manitou granite that may be about 60. It depends on how you want to interpret the zircon data. It's lousy, trashy zircons. But it's parked right next to the Carlotta deposit. And I think in part hosts it. But I would need to know a little bit more about that. And then there's this oddball thing that I looked at way back in the day associated with the north end of the Solitude granite in the northern Pinals. That one is a little bit unusual because there's not a lot of chrysocolla there, but there is these little azurite balls hosted in kaolinite matrix and no sulfides. And that's been heavily drilled. Nobody's ever found a chalcocite blanket. And then there's a solitude magnetite copper occurrence associated with the Solitude granite. And you wonder about what Van Dyke is. There's a porphyritic biotite granodiorite dikes that may or may not be Solitude. They also may be the G porphyry of the so-called Schultz granite. And it's peraluminous. And again, chrysocolla hematite with azurite malachite. And then some veins over to the west of the Van Dyke, which is the New York. And then another funny one that was always, I never really could get it classified right, is the Zonian deposit up in the Yavapai County. And it's a big chrysocolla deposit with hematite. And I might say that one of the main alteration minerals you see in this, especially if you oxidize them at all, is a lot of kaolinite with a little bit of malachite azurite. It's a biotite granodiorite there, but it hasn't been dated, so I'm not sure what it is. I'm guessing it's going to be laramide, probably 70-ish. Next. You can see some of the open pits. The Zonia deposit we just talked about over there in the lower right, and the Carlotta in the lower left. And it turns out there's several prospects in the Vulture Mountains, and I think that it doesn't turn into a regional park or something. Could be something to look at. We always thought that the granodiorite batholith there, the Wickenburg batholith, was a typical laramide pluton, but it's got one potassium argon date of 68.4 million years, and it's a medium grade granite or granodiorite. There are quite a few pegmatites in it. Relatively undocumented, but there's a number of chrysocolla hematite occurrences in there, some of which have been drilled and some of them which could be economically interesting. But again, it's getting close to Wickenburg, so fun and games with humans. Although the current political environment might allow more exploration. So 16 additional peraluminous oxide Greisens that we've seen outside of Pinal County, adding up to about 30 systems statewide. Okay, now we're going to look at some of the regional tectonics associated with these things. What's my time, by the way? How much? Oh, okay, we're right on time. Okay, so next. So some are economic. Again, just to re-emphasize the Texas Canyon Gunnison occurrence. So this mass balance by Fitzpatrick, using 7 kilometers by 11 by 2 kilometers deep. It's certainly deeper than that. I don't know whether it's a sill or not. It's sort of a ovoid shaped pluton, so it may have deep roots. The arrows are showing some of the differentiation tracks and some of the peripheral skarn deposits, low temperature skarn. Now, one of the things about this is that this is different from the Johnson Camp zinc copper skarns, which are associated with hornblende diorite bodies, like the Peabody sill. I think that's a separate system. And there are inclusions in the Texas Canyon Pluton itself that are hornblende diorite xenoliths, which is not a primary autolithic mineral. It would be pre-Texas Canyon. I think they're part of this dioritic system, monzodioritic system. They're quite potassic, that's associated with Johnson Camp. So you've classic superimposed metallogeny here. Again, the amount of it, if you use 21 ppm and you calculate that over that volume, that comes up with 8 million tons of copper, of which about 3 million have been drill indicated or mined. And the large size of these deposits may be in part explained by the large size of the spatially and temporally associated peraluminous pluton. That's from Cooper and Silver, 1964. Great geologic mapping, by the way. I really like that, what those guys did, and Cooper in general. He was a great observer. The giant Gunnison Burrow South Star copper oxide system forms a low temperature system that goes around the whole thing. And there certainly could be up to 8 million tons of copper in there. So this is trivial. The question is, are there other ones? Well, we don't know. This is a brand new model. It needs to be looked at. Okay, move on. I won't spend a lot of time on this slide. This just compiles you can look through it at your leisure, and the PowerPoint that I think is online. The main thing I would emphasize here is look at the dominance of copper. No lead, there's no zinc in this part of the system. These things, even though there was Johnson Camp nearby, nobody ever produced any zinc from these skarns that were snuggled up to the Texas Canyon Pluton. Bit of gold, bit of silver, but really you just are overly impressed with the dominance of the copper resource. Even more so than in the standard porphyry copper. Okay, next. That's the production. This is the resources. None of those guys, they're all, who knows how much could be there, and those other ones we don't have them listed because nobody's drilled them out to come up with any resource statement. But you can see what's going on at Gunnison. Not a trivial amount of copper. Now, all of that, most of that's going to be leached, accessed by open pits. And the leach technology is probably going to be a little different because of the aluminum-rich nature of some of the host rocks. Muscovite gets out into the skarns. These are muscovite-rich skarns as well as your standard garnets and tremolite, things like that. But a lot of soluble copper. That's how they're going to go get these things. So you're not, the good thing about that is you don't have to build a big sulfide mill complex or anything like that. It's basically build a good leach pad and just recover it with leach technology. Okay, next. Okay, now we'll get into some of the tectonics. So these things, in terms of the dating that we were summarizing in previous slides, are late laramide, and they occur in what Jan and I referred to back in the day in 1985 and 86 as lower plate windows of crystalline rocks that were sitting northeast of the outcropping leading edge of a major southwest directed thrust system that, as you can see in this slide here, this is a cartoon just showing you flat subduction. And that's the other thing, is that when the subduction zone got really flat and you got the slab fused tectonically with the overriding southwest directed North American plate, you got a huge amount of dehydration, and that water flooded the upper plate, and you melted a lot of middle crustal or lower crustal rocks, made these peraluminous plutons, which moved up into the mid-upper crust, released their volatiles under depressurization to make a lot of what we're looking at here. And then you uplifted these things later during the mid-tertiary tectonics. Dan and I have referred to that as the Galliera orogeny, and exposed them in the cores of these anticlinal uplifts as lower plate windows. Now, in 1985-86, that's what the situation was, and as you'll see in the next few slides. You want to put the next slide up? What's going on back there? So this is the, in Pinal County again, we come back and look at these lower plate windows. Now these lower plate windows, that's a list of them down there below and in the acronyms, and again you can look through that at your leisure. It turns out the Little Dragoon window, Little Dragoon Mountains, is another window which is sort of an extension of the eastern Rincon Mountains, and you can see that red blob in there, which is the Texas Canyon Pluton. And basically, where it's exposed, there's a tectonic boundary around the thing, and then an inferred one for about 2/3 of the circumference. Okay, next. So let's just run through some of these bullet points. Lower plate windows consist of more frequent and larger areas of crystalline rocks than areas referred to as metamorphic core complexes, or MCC, in the literature, where typically what was emphasized was myelinitic rock fabrics as the main criteria for MCC identification. Well, the rock fabric is not really a rock, it's a deformation fabric superimposed on a rock. But when you go into the geology of these lower plate windows, the principal citizen of that are these peraluminous plutonic rocks. Not metaluminous, you will see some, but they're about 80% of the volume of the plutons that are in there. They constitute the main rock type, and they're genetically linked to the crustal thickening and hydrous melting induced by the Maricopa thrust and flat subduction, which is driving the whole thing. In fact, the Maricopa thrust is basically an intra-North American plate fake subduction zone. We think it may have had as much as 200 kilometers of slip on it. Certainly a minimum of 50 kilometers. Now the other thing is that all of these areas, including the myelinitic rocks, are characterized by reduced radiometric dates, which affect all the other rocks in the in these crystalline complexes in addition to the myelinitic rocks. And that to me is a major character that allowed us to extend the domain of the lower plate. And we've already talked about the myelinitic rocks, which are common in the lower plate windows, but they're only about 30% of the area. Lower plate crystalline complexes do not contain volcanic or supercrustal volcanic or sedimentary rocks in depositional contact with the crystalline rocks. So these things have come up. Typically the PT data on the 2 mica granites, the peraluminous plutons, which has been worked out in several areas now, is running from about 10 to 15 kilometer depths. So you brought this stuff up, and that's why it's not in contact with the sedimentary rocks or the volcanic rocks. And that's another thing about the 2 mica peraluminous guys, is there's no volcanism that anybody has ever been able to show that is on the timeline with these things. They're a completely different animal. Compared to the metamorphic grade in the lower plate, when you find it, you find things like, you find cordiorite, you find anthophyllite, and in particular you can find sillimanite and lucite, the aluminosilicate assemblage, that you do not see in things like pinal schist in the upper plate. The pinal schist in the upper plate is basically lower green schist chlorite stable grade, not upper green schist grade or lower amphibolite grade. Basically the melting temperatures for the 2 mica peraluminous guys that are around 650 to 750. So this is they are a mid-crustal phenomena. Okay, next. This shows from Gottardi et al. 2020 the classical approach to metamorphic core complexes. The red areas are the myelinitic rocks, commonly shown with a detachment fault. And you can argue about what these detachment faults are. I think they're reactivations and denudational features of former thrust faults, mainly the Maricopa thrust system. The other interesting thing is I don't know enough about the geology of these guys down here, but there's a lot of southwest directed myelinitic fabrics that indicate they might be windows in another thrust, which would be somewhere to the west. That would be an analog to the Maricopa thrust, but we just and there certainly could be peraluminous copper deposits down there, but I just don't know enough about that. Although we have done compilations down there, and it would be very interesting to look through them to see if we have any of these in that terrain in Sonora. Certainly the porphyry copper deposits go down there. Next. Now we're going to throw what are more expanded definition of the lower plate of the Maricopa thrust, which are the pink areas, and you can compare and contrast them with the red areas of myelinitic rocks, and you can see that the myelinitic rocks are about 30% of that. So you need to think about these things in a broader perspective. And again, emphasizing that when you look in those lower plate windows, the main volume you're going to see are these peraluminous granitoids. You drove through a bunch of them going up to Phoenix, the secatons. They're a lot more common than people know. And so next. Okay, now we're going to look at, this just refreshes our mind on the Pinal County stuff. And in the next one, we're going to look at compare and contrast metaluminous porphyry coppers, traditional or conventional, with peraluminous. Next slide. Oh, before we do that, This is one of the newer ones that were identified since Jan and I did our original compilation. Of course, and a lot of other people were just piggybacking off of a lot of other science that has been done in the Pinaleno and Santa Teresa mountains. That little blue area up there is a newly identified laramide 55 million year old peraluminous granitoid suite called the Rieno suite, which is thought to be a direct analog for the peraluminous granites in the Santa Catalina mountains. Okay, next. So again, we're just refreshing your mind on, this is now the more expanded definition of these things, using areas of reduced age dates, etc. There's a criteria that we talked about earlier. One thing that was really important in this was the Anschutz AZ1 drill hole that Phillips drilled in about 1990, 1991. They drilled it north of the Picacho, which is this area right here. That's the Picachos. And we didn't put the drill hole on there, but we will in the next one. And the point is that it went through a big thick package of upper plate rocks, through a major low angle fault zone, and into myelinitic rocks in the lower plate at about 10,500 feet, and stayed in them until about 18,000 feet. So in other words, 1061 feet is when it hit the, what we think is the Maricopa thrust. We'll get a seismic view of that in a second. And TD'd at 18,031 feet. That's still the depth record for Arizona drilling. All in the name of trying to find a drop of oil, which they didn't. I had a lot of fun with that. I was the designated, and I knew nothing about petroleum geology at the time, but I've learned a little bit since. And so I kept an eye on that thing for the Bureau of Geology. Then Larry Fellows. Lots of fun stories associated with that play, but I won't get into that. Okay, next. So this is the blue is the peraluminous copper, guys. The one that I showed you up front, that's cornucopia right there. There may be more of them out there, but that area needs a more proper exploration look. And then you've got the blue ones down there in Pinal County and down ultimately down to Gunnison Copper at the southeast end. But you can see that they show a very strong correspondence with the geography of the lower plate windows. Whereas the porphyry coppers are all upper plate features and occur in the lower metamorphic grade upper plate rocks. Other than the Marble Peak and Boomin Canyon skarns in the Catalinas, those are the only ones that we know of that, and we think those might have actually been subducted by the Maricopa thrust system and then have now popped up in these lower plate windows. So this is a whole different animal that is down there, and chrysocolla is the main feature, the main ore mineral. Okay, next. Where's our guy back there? Okay. So this again is back into Pinal County. We're going to look at some cross sections just to get a sense of these things. So the next slide will show the seismic section. Let's back that up. Let me show you where that is. I'm going to take a look at this thing. And that red star is the AZ1 18,000 foot drill hole. Another interesting thing is that over at Sacaton, Dan Laux could give a talk on this, and he should, on this infamous basement fault. And I think that's an analog of the piece of the Maricopa thrust system. And those two guys are all those three main systems there. Casa Grande on down to having a brain fart right now. Santa Cruz, god damn it. What's the one in the middle, Dan? Oh, you know what it is anyway. It's not the two Casa Grande guys are rather Cactus now, Cactus Central, which is the pit, and then there's a northeast one which may or may not be a mine, and then what's the middle one, southwest of Cactus? Yeah, that's it. Okay, so now let's take a look at this section, give you an idea of what this looks like seismically. Next slide. So there's the AZ1 drill hole, and at 10.7 it penetrated through the what we think is a strong deformation zone that separated the upper plate, mainly oracle granite, which is relatively unfabric in terms of reflecting horizons, from a highly reflective basement beneath what we think is the Maricopa thrust. The white lines there are the old Anschutz northeast directed thrust interpretation, and frankly I just don't see any evidence for that in the reflecting data, whereas the first order contrast is this thing, which is a northeast dipping, probably southwest directed, it fits a southwest directed thrust fault. And they intersected two mica granites down in here that dated it around 47 MA, same age as the Peraluminous granites up in Windy Point and in the Central Catalinas. But the point is that this was well north of anybody's standard metamorphic core complex, and they show that this terrain may exist under much of Arizona. Okay, next. So back in 1984, I was aware of this since I'd been following closely the AZ1 drill hole. And so I just put together a cartoon, and now I'm superimposing the peraluminous and metaluminous copper story on it. So the peraluminous guys are these little blue guys. And as you can see, one of them is using the North Star fault zone. And here's the Little Hills guy that we talked about earlier, using the Mogul fault. So some of these things leaked up these high angle faults, which typically dip south. But an interesting thing about them is that they've all been thought of as normal faults, because you see metamorphosed Apache group over here and Precambrian oracle granite over here. Well, that's a normal juxtaposition. But if this is a lower plate that's been shoved up against, and this is upper plate, then that becomes a large-scale reverse fault. And that happened in the mid-tertiary. That's not only way you can drive things like that, as well as the Romero Pass fault, which has also been shown to have a reverse fault juxtaposition in terms of offsetting different sills in the Catalina 4-range gneiss to main range. And then you have the Mogul fault here, the reverse faults. And then the classical San Manuel, that's been offset by a low angle normal fault, which then became a preoccupation of the exploration community looking for more of those. And to some extent, you got to be worried about this whole other story that's in here now. that is not a normal offset story. And you're bringing mid-crustal peraluminous copper stories with chrysocolla in them up. They're not deep porphyries, and they're Greisens, which is not the kind of alteration you see in a porphyry. And so you have this classical San Manuel situation, which turns out to be quite different and anomalous to many of these other things. So you've got to think about that when you're out there exploring for copper, which I think there's going to probably be another push here in the next few years. Okay, next. Next slide. Okay, let's get into the copper source a little bit. How much time we got left? Okay, I'm just about to finish up here. So let's talk about sources. Obviously, it has something to do with the spatially and temporally associated plutons. So the classical metaluminous porphyry coppers are associated with more mafic metaluminous hornblende bearing plutonic sequences in place during intermediate angle subduction in the laramide. And the, come on, did I run out of battery? Oh no. So this yellow guy here is what we've modeled as a high alumina eclogite layer in a layered mantle model in the upper asthenosphere that gets hydrously melted to make these yellow guys, and those ultimately ascend into the upper crust, decompress through a series of gabbro to ultimately quartz porphyry. Well, basically gabbro, quartz diorite, pyroxene quartz diorite, hornblende diorite, hornblende biotite granodiorite, biotite granodiorite, bingo, porphyry copper, and then late stage quartz feldspar porphyry, which leads to late stage veins like you have at magma. And a mantle source for the copper. Peraluminous, that's what happens in the late laramide. Now you've got flat subduction going on. And you've got this water flood that's coming off the flatly subducting slab, possibly from dehydrating metagraywacke materials, which we know got all the way under the Colorado Plateau in the Four Corners region. That's because they've seen these eclogites in the diatremes themselves. And you water flood it, and the literature's starting to come up with this, starting to see this now. The lower and mid crust, and you made a lot of peraluminous granite minimum melt. So you picked that copper oxide up from a source in the middle crust. So there's always been this big debate about what is the source of copper. Well, it's not the source. It's a number of different sources. And that's my contribution to the debate. You can't just try to go for one. There's two of them in terms of major ones in Arizona geology. And there's other ones if you go planet. But, so that's the laramide story. And you're doing that under granite minimum melt conditions in the middle crust. Okay, next. So back to copper Greisen exploration opportunities, which take us back to the first slide. And so in this particular case, you can walk out here and literally see anatectic melt textures of the Orocophia schist that coalesce into a peraluminous pluton. It's a two-phase thing. The biotite granodiorite in the lower part of it is associated with the copper, and then the upper part of it, in that sort of purplish color, is a copper gold minor bismuth system. And that's what a lot of the gold deposits that we originally thought were peraluminous gold, and they are, but they're associated with more differentiated peraluminous plutons. For example, the one at the Vulture mine in Wickenburg, but also Gold Basin is another really good example of that. Okay. Next, final slide. Sum it up. Copper oxide deposits are found in or near lower plate windows in lower plate crystalline complexes. No classic porphyry copper deposits. Found in lower plate crystalline rocks that contain peraluminous plutonic rocks, which constitute the main rock and are genetically linked to crustal thickening induced by the Maricopa thrust. Stage 3 biotite granodiorite to stage 3.52 mica granites are more specifically associated with peraluminous copper-oxide Greisen deposits. Coarse muscovite iron oxide quartz Greisen is the main alteration type. Other peripherally associated deposit types are various physical formats of tungsten, beryllium, and gold deposits. Quite a bit different than what you see around the edge of a standard porphyry. Good luck and happy hunting.
Right on time, thanks.
Amazing.
So, Ed has a microphone, and I do too, so if you have any questions for Stan, or you want to harass him in any way, feel free.
Yeah, Mr. Aiken, he always has to. He's taken over for me in terms of the questions.
It's to keep my brain from atrophying. So I had two questions. One is, does the leatherwood have a further evolved biotite granodiorite that is copper bearing? Number one. And number two, on the instance of the Gunnison and the east side of the range, the Little Dragoons, where the Gunnison has the skarn, does that wrap around to the west symmetrically and then get detached into the San Pedro Valley, or did it ever exist in the Paleozoic sediments that extended over there? And great talk, Stan. Thank you.
Okay. To your first question, rephrase that again.
Okay, well, the leatherwood is a
Okay, I got
biotite
it.
hornblende.
Shut up. Okay, now I'm on it.
Okay. You're always so elegant.
Just having a little fun with you, Dan. Okay. Tom Heydrich has a map of the leatherwood around where the skarn is at Marble Peak. And it does go to a biotite granodiorite. With the main pluton, 80%, almost 90% of it is a biotite hornblende granodiorite. So it evolved into this. When it evolved into the biotite granodiorite, there was a big fluid release that ultimately hit the Paleozoic reactive rocks. And these are lower Paleozoic rocks, which is an interesting thing which I shouldn't get into. Made the skarns. Now, the other interesting thing about the leatherwood is it's the only diorite body in Arizona, or anywhere else for that matter, that has these really nice little glassy green epidote crystals in it, which are not, I don't think, standard propylitic epidote chlorite calcite alteration. I think that when that thing got subducted, it got pressurized, and the epidote got recrystallized into a high temperature epidote, and Lawford Anderson proved that with PT. So everybody was wondering, and there are a number of other epidote bearing rocks, like in the San Gabriels and Mount Low granodiorite, that where the epidote indicates deep, high pressure stuff. So that's what I think happened there. And that's related to the emplacement, because by then you were at 10, 15 kilometers with the peraluminous story coming in. The Marble Peak formed at about 3 to 5 kilometers. So you added about 5 to 8 kilometers of stuff on top of Marble Peak via the Maricopa Thrust in the late Laramide during the flat subduction event. Okay. So, now we're back over to Texas Canyon.
Yeah,
The northwest contact of the Texas Canyon Pluton is mapped by Cooper and Silver as Pinal schist. So you don't have the opportunity there to make a skarn. There are some minor tungsten, and the other thing over there is that for the most part, the stage 4 tungsten deposits, including the Tungsten King off on the west side along the Tungsten King Fault, are probably related to this stage 4 Texas Canyon Pluton. So that part of the Pluton is too differentiated to make peraluminous copper deposits. The stage 3 on the other side, on the east and north side, is only in stage 3. It's biotite, granodiorite, biotite, apatite. There's two main kinds of apatite in there. A really good thesis on this is Fitzpatrick. He really tore up the Texas Canyon Pluton and figured a lot of what's going on there. And he has mineral chemistry. It's a great thesis. So read that. But so the bottom line is I do not think that there was something that got sawed off the top of the Pluton on the west side and is now under the San Pedro Valley.
thank you.
Any others?
Good evening, Stan. Nice talk. So I have a question about some of your slides. You say that copper deposits are associated with stage 3 biotite apatite. So
And biotite granodiorite.
Okay.
But the big one at Gunnison is biotite apatites.
So do you mean it's mafic-rich apatite? What do you mean with?
No, it's just the biotite is an accessory mineral in quartz feldspar apatite, which is about 70-75% silica.
Okay.
So these are your kind of standard biotite apatites, but not. And then it evolves. What happens in the Texas Canyon Pluton is very interesting. The timing, and there's good dating on it now. It's 57 to 53, and it has been placed over about a 3 to 4 million interval right across the Eocene boundary. And if you look at the orientation of the biotite apatites, they are kind of east-northeast apatites. And then the apatites associated with the tungsten mineralization are due northeast. So there was a stress change that's right at 55 MA because there's a good RBSR tight isochron of about 54 million on the stage 4. Whereas the zircon dates on the main phase of the Texas Canyon are about 57 to 55. Two of them, one by Chapman and one by the guy that did the biotite apatite. Is a master's, undergraduate thesis out of the U of A. Jan, do you remember the name of that guy? Started with an H. George Davis student. But, God damn it. Anyway.
Okay, thank you.
Hi, Stan. Thanks. That was an interesting talk. I've got a lot of questions, but I'll try to boil it down to a couple. But one of them, sort of early on, is you were talking about the association with the crystal and specularite and so forth.
Yeah.
So one of the things I've seen a lot, and I've been to pretty much every one of your examples up there, except for a couple. So, but a lot of times in these systems where you've faulted and tilted the systems, and you're looking at sort of deeper flanks, as you go outbound to systems, you go from more sulfur-rich assemblages out to iron oxide assemblages on the flanks of porphyry systems of all ages, whether they're in the mid-late 50s or into the 70s.
Yeah, there's a lot of other specular hematite occurrences
Yeah,
out there.
and so you know, you've got the source of copper from the weathering systems. The example you showed earlier, you've got botryoidal chrysocolla sitting on top of specularite. That doesn't have to be, you know, an assemblage. That could be later, much later. I mean, there's no reason that stuff couldn't have been 30 or 50 million years younger than the specularite. There are some examples that you were also giving where you could be dealing with some external fluid related things related to tertiary tectonism, where you could make specular hematite at a younger age with chrysocolla as well, with oxidizing sulfides. Why are you, like, like in that photo example that you gave, for example, why do you have to call that an assemblage? Why can they be totally unrelated? Copper from nearby just precipitated later on that specularite.
Well, the other thing that you find, that was from the Burrow Pit at Johnson.
Yep.
And
seen that actually, yeah. Anyway, so.
In that same area, quite close to where, well, even almost coexisting with some of the chrysocolla, is you have Goshenite beryl. So you have some of these really high temperature Greisen type mineralogies that are coexisting with it, not just the specularite, but on a regional basis, the specularite chrysocolla is a really consistent association. And the other thing that I'll add to that is that almost all of these things are found in peraluminous host rocks. So the other hematite occurrences that you're talking about, because there's been lots of hematite out there, don't have that peraluminous granite association.
All the porphyric coppers too. The example you give up by globe, the Manitou, for example, that is, it's an interesting, because it's not clear what the age is. It's been dated as Precambrian, but it has ages that suggest it could be Laramide too, really
That's
poor
right,
zircon
that's
dates.
correct, right.
Who knows what that is? But
It's
that
trashy
thing looks
zircons.
very different from a lot of the stuff in the district, and it's got some oxide copper in places, but it could be, again, secondary oxide copper coming in later on top of the other.
Well, that is the standard traditional explanation for that, as well as other ones. But they've never really plugged in these, because the Manitou granite is, even though the dates stink, although they could be as young as Laramide.
Could be. Might be old. I guess it might be older, but we don't know.
Yeah, you'll have to ask Eric Seedorf about that.
It's a weird one, though. By the way, so you've been up there with Eric?
Not there, no.
There's really nice aquamarine crystals in there, in nice pockets.
Yeah. In the Manitou?
In the Manitou, yep.
Yeah.
So.
Wouldn't surprise me.
Yeah. Interesting one, too. So another question I have, too, this is another total different direction, but it kind of caught my attention when you were talking about it. So you were mentioning seeing a thopholite and cordierite in places, and I can tell you I haven't really been out looking for that in Arizona, but where? Because I haven't seen that. And that's interesting, because the interesting thing about that is it's not just a metamorphic mineral, but it's a magnesium metasomatized rock.
That's absolutely right.
To get that, and so you usually see that in like a volcanogenic a deposit or seafloor hot springs where you've got magnesium metasomatism of a rock that'll tell you what zoning you're seeing in that.
Okay, this particular occurrence that I was alluding to is porphyris in the Merida Formation in a big inclusion floating in the Texas Canyon Pluton that was documented by Cooper.
Interesting.
Yeah.
Okay. Where is that in the Texas Canyon Pluton? That's
down near the Centurion mine.
Okay. All right.
And there's two occurrences there. There's the Merida near the Centurion, and then there's another big inclusion that's sort of spans the interstate.
Okay. That's
and that one has silmonite. The anthopholite is one in the one near the in the Centurion thing, and that's all chopped up by thrusting, by the way.
Yeah. So things like the silmonite and like andalusite and things like that you'd expect in that kind of environment, but to get the anthopholite and cordierite, you'd have to have a lot. Like
well, the thing about those is, they're magnesium, but they also have aluminum in them.
Yeah.
And I think that could reflect some aluminum metasomatism related to the Pluton injection itself.
Okay, interesting. All right, that's a new one for me. Thanks.
Yep. Now.
Yes, thank you. You normally associate chrysocolla with a low temperature system.
Right.
What do you think the temperatures are that cause that chrysocolla to be deposited there, and at what depth do you think that may have happened?
Well, I think it's deep.
How deep?
10 to 15 kilometers. Now, I have nothing to prove that other than an association with hematite, which is an accessory mineral in the plutons, etc. However, there's an interesting mineralogy story that has, if you go over and look at some possible analogs, like with quartz, really high temperature quartz above what I refer to as a crystal window, things like cristobalite, and they form as globular balls in things like obsidian nodules. Uh-oh, I can see that Alfredo is checking his book on me. And so the idea is that at really high temperatures and high energy conditions, before you consolidate down into a crystal structure, things are existing as high temperature colloidal gels. Now this is all speculative, but it's just based on natural history observations of other high temperature situations. So, and this overall association of chrysocolla and 2 microgranites, etc. So that's all I can do on that one for you. It's something to follow up on, though, because there is some literature that does look at silica activities, etc., and then says that, yeah, there could be a possibility that at higher pressures you could stabilize this stuff.
Would there be pore spaces for those globules to grow at that kind of pressure?
Well, again, if you go up, yeah, I have no problem with that, or forming breccias or anything like that. If you get the water pressures high enough in these, and boy, these things, to crystallize and not release any volcanics, you got to have a lot, the water pressure equilibrates at, say, 10 kilometers, but once you get a hydrofracking event, you can go brittle. You can produce brittle textures, and if you don't believe that, just go up and look at that pegmatite near Summerhaven. Those pegmatites are broken up, and you'd think, my God, that thing is some kind of a fault pressure that formed at 2 kilometers or something. But that thing probably cracked itself up at 10, 15 kilometers. And again, high water pressures will do a lot of, in a lot of pegmatites, can produce really nice breccias. So I have no problem with brittle fracturing in open space. I mean, take a look at the cavities that form in some of the pegmatites, like at Pala in San Diego County. You make these big old, and those pegmatites came in they were deep. Those cavities were deep. So I have no problem with open space in those kinds of conditions.
Maybe time for one more question before we, if otherwise, let's thank Stan for.
Nobody on nobody out there
no, there aren't any questions online.
in electronic land.
No. Okay. Well, thanks again,
Hey,
Stan.
thanks for the discussion, guys.
Hey.